Hello, y'all. This is Darrell Lee Berry Jr. back with some linear algebra. I'll be doing some background. The stuff we're doing right now mentions again the four fundamental spaces. So I'm going to go into a bit more detail to refresh myself and clarify what's going on with that. And also, what I'll do is I'll move on to how to discover a basis. So that's going to be all in section 3.2 and 3.3. So the fundamental spaces won't directly be from the book. Uh, it'll be basically trying to expound upon some notes that we received in class. And 3.3 will be directly from the book based upon one of the homework problems that we received that's what assigned from the problems in the book. So eventually I'll do that problem as well. So to start with the uh, illustration or demonstration, as we call it. Won't be needing the book today. Well, I'll bring it back up later. Right. And this seems to be working properly. So we have the four fundamental spaces. And I guess it's best to start with we're dealing with this. So this is actually a plane. This equation relates to a plane because we end up having uh, some matrix. Let's say that this is a 1 by 3. I don't, that'll be bad. Say a 3 by 3 and a 3 by 1. So this will equal also a 3 by 1. Because as we reviewed in previous videos, the numbers on the outside of here become the result, and the inside has to match in order to multiply those things together. So this would be a 1 1, a 2 1, a 3 1, because these are the rows and these are the columns. So I'm still on row 1, column 2, row 1, column 3, row 2, column 2, row 2, column 3, row 3, column 2, row 3, column 3. So I guess technically it's to be a hyperplane, but I wanted to start with this because they're going to expand on this. So if I was to multiply this out, we would have x1, a11 plus x2, a12 plus x3, a13 equals b1, x1, a21 plus x2, a22 plus x3, a23 equals b2, and x1, a31 plus x2, a32 plus x3 a3 equals b3. All right. Now, we know from uh, our previous videos that x will be some grouping of numbers that are real. So we'll say xi are real numbers, and I equals integers from in between 0 and 4, so from 1 to 3. And we can say that thus these are the normal vectors. So the normal vector 1 from the first row would be a11, a12, a13. And these would be the normal vectors for these three planes. Now, it would actually take getting some numbers to see how they relate. Perhaps they describe the same plane, or perhaps they describe intersections of planes. But we could see how each of these uh, outcomes is a plane, because we have the normal to the plane, and then we have, let's say, well, all the x's will be the same. It's just for the system to work out. The only x1s and x2s and x3s will work are the ones that the same x1 and x3 complete all three of these equations at the same time, but we're not worrying about that right now. We're just taking out just one of these and saying that's a plane. So what we can do here, we can say, and basically trying to extrapolate what's in the image here, we can say that this is x. So we know that x will have two components to it. One that's going um, horizontal and one that's going vertical, let's say. So it looks like the book calls these the row spaces and column spaces. So this will be row space, and this will be column space. So x equals xr plus xc. Well, actually, they do it slightly differently. They actually break it up into the null space. So hold up, let me erase this. I mean, that is true, but that's not how they doing the fundamental spaces. It looks like what we need to do is say this vector x. So I'll make this in green. So we can say x is a vector, as we said, that solves this entire system. X is one set of numbers that can make this entire system work. So we can say that x is going to be the solution to the homogeneous equation plus the solution to the uh, general system. So if we was to, let's say, if I was to take just this first one here and say Well, I guess I have to take the whole thing for it to work properly. So we'll take this whole thing again, and we'll just say instead that that's equals to 0. So if I were to copy this whole thing down, except there will be zeros at the end, I'll end up with an augmented matrix. If I was to solve this, that would look like this. And when I do row reduction, I'll end up with an x. I'll call this x n equals x in 1, x in 2, x in 3. That solves this system for 0. And at the same time, if I was to bring the original one down, I'll end up with a solution to the general, where let's say if I pick certain numbers for b, I'll end up with an x that solves this. So we can say x r equals, and let's call x row space, equals xr1, xr2, xr3. So we know from our earlier videos that if we have a x equals b and ax equals 0, and we say that u solves this and v solves this, that we was to add these together and say au plus av equals b plus 0, so that equals b. So we could also say a u plus v equals a u plus a v, which equals b plus 0 equals b. So what this means is that if u solves the general and v solves the homogeneous, then u plus v solves the general. And the u, the one that solves the general, they call the row space. And the one that solves the homogeneous, they call the null space. So I imagine that it's called row space because when I actually multiply this down, the x values become a row. And that row that's the sum of that row is what ends up being or summing to b, and x, all the values of x has to be such that with those values of that row of the A matrix, the respective value of B1, B2, or B3 is solved. So let's take a look at this and draw this out some, being that we have this understanding. So this is the row space. and this is the column space. So row space is this. Excuse me, and this is the null space. Null space is this. And currently, the row space and the null space will be orthogonal to each other. But the question is, why would that be? So we have from earlier AX equals, because I've confirmed that these two together solve the general system. So I can say A, and I'll use my same, actually, I will, I'll use my same iteration. So U plus V equals AU plus AV. But we know since the first one equals 0, this equals AU, since the null one equals 0. So well, the process is slightly more clear, but there's still a lot I have to get clear about the null space and row space. But this at least is getting us in the right direction. And these two are supposed to be right angles to each other. So this would make X equals U plus V. X solving, well, maybe I should make a different symbol for X. But if we're considering the general solution that works. So what I'll do now, I'll bring up the book and I'll see if this slight clarification helps at all with understanding what we're about to do here. So this is 3.3 in the book. Linear independence and basis. So we'll read through this part, and then I shall likely be back later. In view of our discussion in the preceding section, it is natural to ask the following question. Given vectors v1 all the way through vk are an Rn, and v also an Rn, is the vector v within the span of these vectors. And it says, of course, you recognize that this is a question of whether there exist scalars C1 through CK such that, so I'll say does V equals C1 V1 plus C2 V2 plus C3 V3 onto plus CK VK. If that equals, then V is a scalar of all of those vectors, is in the span of all of those vectors. As we are well aware, this is in turn a question of whether a certain inhomogeneous system of linear equations has a solution. So this is the same thing as saying, does a certain system of inhomogeneous linear equations have a solution? So in a sense, I imagine V would be the solution of that. So this would be the same thing as saying V, or I should say V1, V2, VK, C1, all the C's equals V. So this system of inhomogeneous equations, because basically C would go ahead and matrix multiply against all of those, and you would end up with this. And basically, if I was to condense all of these into one vector, we would end up with C1 V1 plus C2 V2 plus all the way on to V. So the system of equations and V CKVK equals V. That's the last one. So what we're saying basically is if you can solve this system of linear equations for some values of C that solves with V being equal to that system, then we know that V is in the span of that system. Simple enough. If you have any questions, be sure to ask in the chat or comments. And give me a moment, let me check my everything seems to be going okay. Any issues, let me know. So as we saw in chapter 4, part 1 is often interested in the allied question, and also is it a unique solution? Which would be the vector V. So here's an example. Where the system is inconsistent. And let me see if we should do this example. trying to find an example where we find a basis. Okay, here we go. This is on page 149. Let me share this page. It says definition. And let me see what's ahead of that. Right? So definition. Let V be a subspace Rn. And as a reminder, V being a subspace means that there's a zero vector in V. There's closure over some, meaning you can add two different elements of V, and it's still a subspace of R. Is still with a subspace of Rn. And we could also scale any subspace or any component of V by a scalar real number, and it's still a subspace, still within that subspace, or still within that, still within V. It makes it a subspace. So V is a subspace. We can say that the set of vectors V1, Vk is a basis for V if and only if 1, V, looking at this line right here, if and only if V1 all the way to Vk span V, which is to say V equals the span of V1 all the way to Vk, and 2, the set V all the way to Vk is linearly independent. So, two things we have to test to solve or prove whether something is a basis. We have to check that the vectors in question span the entire subspace, and we have to check that each of the vectors are independent of each other. There's linear independence where one of these vectors can't be a scalar of one of the others. Or at least perhaps we can combine two of them to, make a vector of a lower space, but that won't be the question that they ask. So to give the example 6, E1 equals 1, 0, 0, 0. E2 vector equals 0, 1, 0, 0. And En equals 0, 0, 0, 1. And these vectors are in. So the assumption is that each subsequent vector has a 1 in its subnumber, and all the other numbers in that vector are 0. Then we can say that the set E1, E2, En is a basis for Rn called a standard basis. And I imagine it's called a standard basis because each of the components are one. So if one of those was a different number, then it would scale essentially whatever number we put in. So we put in one, we get one along that direction. If you put in two, we get two. If a two was here, if I put in one, it will double it. So I have to put in 1/2 to get one. So this is why ones are a standard basis. And to check this, we must establish the two properties above hold for V and Rn. All right. So one says that V has to equal the span of these vectors. So does V equals the span of this set of vectors. And again, we're checking to find or confirm a basis. So let's see. They say for one, if x equals x1, xn in Rn, then x equals x1 e1 plus x2 e2 plus xn en. So we can see that we have enough vectors for every single value of n in Rn. So this set of vectors does span the space. And then for 2, we can say, suppose C1 E1 plus C2 E2 plus C3 E3, let me make that n equals 0. The only way for this to be true and be linearly independent. Hold up. Let me fix my screen share. All right. So suppose C1, that combination equals 0, since Each of these has a 1 in it, and this has a 1 in it, and this has a 1 in it. Now, it does bring the question, what if we have a situation where we have an even number, C1, E1 plus C2, E2. Well, if C1 was 1 and C2 was -1, that would actually equal 0. Oh, but this is a vector. You have to remember that this is a vector. So this would have to be a whole bunch of ones. This would have to be a whole bunch of negative ones, but that's not what they gave us. They gave us E1 is 1, 0, 0, 0. And let's say we're just doing 12 of them. This would be 1, 0, and this will be 0, 1. So we make them be anything other than 0. Then we would have something there. If C1 was 1 and C2 was 1, we'd end up with 1, 1, this vector. Or if C2 was 2, and so on and so forth. So the only way we can make this equal to 0 is if C, the vector C, is the 0 vector. So that means that they are. Thus, the set of E vectors are linearly independent. All right, so since they are linearly independent and they do span the space, the set is a basis vector, at least a basis for V. Simple enough, easy enough. So what I'll do, I'll probably come back, but tomorrow or Saturday, and continue to work on probably the subspace things. I gotta figure the subspace thing out. So we don't have any class today, but tomorrow, because of the holiday, but tomorrow I'll probably ask my professor about that and get more clarification, and I'll come back and talk about that some more. I still feel unclear about the 4 fundamental subspaces, even though I'm inching closer towards an understanding. So be sure to like, subscribe. I'll share my links again momentarily. Help me get to 1,000 subscribers. That's the goal. I'm also offering tutoring, math, science, whether physics or astronomy, up to sort of the middle undergraduate level, GED as well, high school as well. Just contact me through any of my contact points. Also Patreon, and I'll see y'all next time.